let's start. Okay, we introduced integration last time, so let me. So I want to cover Stokes theorem. So for that I will need manifolds with boundary. Manifolds with boundary. Well, it's all goes similar to just usual manifolds, so we'll not repeat all that. We'll just point out differences. So definition is above, but we need to allow well, what's called boundary charts. So what are those boundary charts? They consist of open neighborhood in our manifold and the map, which is homomorphism, and that this map is from U to what's called, we'll denote H map. So this is upper half space. So Hn here is well, tuples x1 blah 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 xn from Rn, such that well, it's half, and this half we divide by the last coordinate, so we have xn greater or equal than 0. And then well, then by definition, the boundary of Hn is just all the same, but here we have equality, xn equals to 0. And so this thing makes it boundary chart if we say that phi of u intersects with DHN non-trivially. So we need, so we have this additional thing. So we have some usual charts, we have some boundary charts. And this being said, we need to understand what is a smooth map from a boundary chart or to a boundary chart. Well, to a boundary chart it's clear about from if we are on the boundary. So that should be fixed. So if I have f, this is from V to Rn, right? And this V is actually open in subset topology in Hn. So I don't know, I need to use different symbol here, just like that, open in Hn. So when, so the question is when such thing is smooth. And then by definition we just say that f is smooth if for any point x in V we have so there exists an open neighborhood V tilde of X, but this is neighborhood in Rn, so bigger. So open in Rn, and extension f tilde of f restricted to v to v tilde, well, smooth extension, such that f tilde is smooth.
Непрерывно, да, чтобы, любой,
Ну,
в частности, оно будет.
в частности, непрерывно, да. Yes, so that's what we want. Then we also need to maybe clarify what is a tangent space at the boundary, because the temptation to call it like a half space, but it's not a half space; it's a whole space. So if I have a P, which is the point belongs to the boundary of Hn, then I just define dfi over dx j at P. Right, if is my map from Hn, right? So I just define it as the derivative of f tilde with respect to dx.
Он такой же по размерности.
Ну да.
Почему он не зависит от продолжения?
Ну потому что гладкое продолжение. Вот, у вас как бы, ну, как бы как у вас, грубо говоря, в направлении к гладкому многообразию. То есть вы от границы можете вот, двигаться в сторону гладкого многообразия. Вот. Так как у вас гладко, если в обе стороны как бы гладко продолжили, вот, то это как бы задает вам производную в обратную сторону тоже. Вот. Поэтому не зависит, конечно, от того, как самому.
May I ask a clarifying question about the definition of smoothness of F? The definition is given for any point x. Is it true that the intersection of the boundary of the half space is non-empty?
Is it necessary still? Yes.
No, we're just considering. We need to define for such open subsets.
No, it's not necessary. V can be
But
yes.
we need to define for them specifically. Like
Yeah,
for-
first of all, I'm saying that P is on the boundary, right? So, and V is V is neighborhood.
If we take x
Right,
that
right.
lies inside V, that is
Yes.
on the boundary.
Yes, so yes, X is inside V tilde. No, it's okay. V tilde will be will have non-empty intersection with Hn. It's okay.
What about V itself?
But V itself is also neighborhood of X, and X is on the boundary of Hn. So you have like
The x
have
is
like
on
this.
the boundary of Hn. It may be on the boundary.
Yes. Well, V isn't yet. Maybe on the boundary. Maybe not. Yeah, but we know that. Well, if it's not, also V intersects with
So,
H. So Hn is this guy.
On the picture, we may place x on that line, that is the boundary, and the function f is smooth if we can extend it to this circle on the bottom
Yes.
of the line.
Yes. Yes.
Okay.
But this definition, if I got all technical details correct, also work for interior points as well.
Yeah.
It will just be smooth in usual sense.
Yeah. Thank you. Just for interiors, the same, like, we don't need to find this V wave because
If you just say that
Just,
it
shrink V, so it will
yeah,
be
so it will be inside, yes.
Okay.
All right. Now, yes, so I never defined what is dm in this case. So dm is all the points p from m such that there exists a boundary chart. So boundary chart. Such that, well, of course, P is inside Q, and also I need phi of P to be on D, Hn. Well, of course, one has to be careful and prove that there is no point which is in, well, there's no point which is boundary and interior point. So interior point meaning that it is like I have really a smooth chart, such like usual smooth chart for this point. So it cannot happen that it is on the boundary and also it has a usual smooth chart around it. Well, something to prove, but well, we'll not do this. Right. And okay, so this are really all the differences. Well, well, if I have a point on dm, then well, TPM really is not a half of space, right? It is, well, has basis. It's really a vector space that has basis, as usual, d over dxi, that's p. Where d over dxi, we define it here. Right. Next thing that I want to say is that now I need consistent orientation. So suppose that I have well,
excuse me, what
yes.
about the dimensionality of the space? Is the same as the manifold dimension or one less?
Of which, of dm?
Yeah.
Well, one.
TPM.
Yeah, TPM is the same as dimension of usual charts. This m, so all our, we always phi maps to Rn, regardless if it's to Hn or Rn, like bigger. So this n is the dimension of TPM.
So the tangent space is not influenced in any way by the fact that P lies on the boundary.
Yeah.
Okay.
Okay. So now what? Yes, I want to say that dm is manifold itself, and it is actually an embedded manifold of m, embedded submanifold of m. And this can be proved by using well, we formulated the case-wise condition for. So again, the definitions are all the same, right? You just need to say the same words for manifolds with boundary. You just need this additional possibility to having boundary charts, right? And what is embedded submanifold? All that is like submersion, immersion, all that you have, and you know. So this should be injective. So inclusion map should be injective immersion, which is homeo to the image. right? And of course, you can prove it. So proved by well, a variant. I would formulate it like that of case-wise condition. Case-wise condition theory. Anyways, we had this criterion for a subset to be submanifold, and it had to satisfy case-wise condition. This all goes through to manifold with boundaries, and then you just use it to see that DM is embedded submanifold of M.
Можно помнить, какой-то condition?
Ну, что у вас есть карты, в которых, значит, у вас под многообразие выглядит просто как, значит, ну, сечение под пространством. Ну вот, то есть вы берете, зануляете там последние координаты, а которые остаются, будут координаты на вашем подмногообразии.
Условия гарантируют, что многообразие.
Да, да.
Всё.
Ну, а здесь как бы то же самое, только в какой-то момент у нас просто в какой-то карте отсутствует половинка. Вот. Окей. So I need that to say that TPDM is a subset of TPM for any P from DM. And so therefore, so suppose now that I have orientation on M, so suppose M is oriented, then so orientation is, we choose a class of bases at each TPM, right? And we denoted it like that. So for any P from M. So this is our choice of orientation. Then define orientation on DM as follows. We just say that, well, our orientation will denote the corresponding orientation OP with this symbol, partial, as P runs through DM. And then I define it like this. So suppose I have V1, V2, some basis, Vn minus 1 belongs. So this is like this representative of class OPD. If and only if the following basis is a representative of class OP. So I take all these vectors, and but the first one I take minus d over dxn at point P. And then I have v1 blah 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 vn minus 1. If this is inside of
So
This
this
sounds
is
neat.
the basis in the tangent space of the boundary.
yes,
Yes, and it has the dimensionality n minus 1.
yes.
what I asked on the previous maybe slide screen.
Hmm?
The same question. You said that
No,
this is-
it depends on how you look at the point at the boundary. Right, so you ask, so it is, there's difference between TPM and TPDM. So this is submanifold of dimension 1 less. So this has dimension n, this has dimension n minus 1. So this should be a basis inside this guy.
So understood.
Right? So in the picture, we have like a boundary, right? And I'm saying that, okay, I'm choosing some basis on the boundary, and it is positively oriented if outwards pointing vector completes it to positively oriented basis in the whole manifold. So that's the risk. Then, well, of course, one should check that this is reduced orientation, all that exercises. But I'll just claim it, and we, by definition, such orientation is called Stokes orientation. So OPD is called the Stokes orientation. One last thing before I can proceed to formulation of the Stokes theorem is that well, of course, I can introduce integration on the manifold of the boundary in the same way as we did for manifolds without boundary. There's no really
Сейчас.
difference. Ага.
Не определяли интеграл.
Определяли. Ну, на многообразии без границы не определяли. Ой, на многообразии без границы определяли, а с границей не определяли. Но я говорю просто все аналогично.
Ну, на прошлой лекции. Можно как бы новую игру запустить.
Просто вообще было
Маленький.
проще. Интеграл.
Да, было дело.
Там просто в каждой карте,
Да не, это да, просто...
Ну, я выбираю там разбиение единиц, вот,
Да.
вот это все, и там. Да. Вот. Okay. So integration is the same, but then also I need to say the following. So if I have so for any omega from it's a K form on the manifold M. And K might be less than the dimension of M, but also I have N, which is submanifold of M. Submanifold. And actually, I don't even need it to be embedded submanifold. I need it to be, well, also oriented. Such, well, oriented and immersed and k-dimensional.
Может быть, ориентация должна быть согласована?
Ну, должна быть, да. Ну,
В каком смысле?
ну, вообще не должна. Мы сказали, что у нас может быть как бы, ну, значит, пока что не обязательно. Вот, я просто хочу сказать, I just want to say what is an integral over a form omega over this M. The orientation may be consistent, maybe anti-consistent, right? I'll just fix it by saying that it is just so I have inclusion map of N to M. It may be orientation. Well, it's like a differ to an image, in a sense, right? So it may be orientation preserving, may be orientation reversing, right? So I have I star omega, and then M.
Ну, только форма, они двигаются в какую сторону? Омега, она на M лежит?
Так, только давайте, да, действительно аккуратно. Мне нужно вы правы. Значит, вот здесь вот надо поменять. Значит,
Ну, это странно.
нет, вообще нет, сейчас. Нет, это просто определение. Вот смотрите, значит, я просто вот это пишу n здесь, а здесь тоже должен написать n. Вот это просто определение, это значок, который не имеет смысла. А вот это имеет смысл. Я говорю, что вот такой символ значит вот это. Вот.
Все равно на ориентирование, да. Ну, как-то ориентирование.
Ну, то есть, если ну, он должен быть, она должна быть мы должны выбрать ориентацию, вот, а там уже вот это сделает свое дело. Тут либо плюс, либо минус напишется.
So originally omega is a form on M,
Yes.
and the definition is given by the integrating the pullback that is the form on M over
Yes.
M.
Yes.
Оно там погружено, да? Не обязательно вложено.
Не обязательно. Okay. Theorem. Stokes theorem. For any form omega, which is, well, I also need here, well, C, which means it's it has complex support. So this thing, because we only defined integrals for forms with complex support. For omega, which is dimension of M minus 1 form on M with compact support, we have integral over M of d omega is the same as integral of over dm of omega. So here we need to specify on dm we have Stokes orientation. On dm we choose the Stokes orientation.
Компактный носитель здесь обязательно?
Yes. Ну, как заметили, я как бы не проговорил в прошлый раз, как правильно заметили, носитель — это замыкание множества, где форма не нулевая.
А почему нужна компактность?
Ну, потому что мы интеграл определяли только для компактной формы, потому что нам нужно было разбиение единицы и конечная сумма. То есть мы значит, покрывали сначала картами омега, потом выбирали конечный под покрытие. Потому что я как бы определяю это как сумма, как сумма по кускам.
Да,
Я хочу, чтобы эта сумма была конечной.
Бесконечно мерном многообразии же, есть тоже, не на компактном многообразии тоже есть разбиение единицы.
Ну, есть. Но просто вы не можете гарантировать, что у вас тогда будет Ну, там нужна какая-то гораздо больше сильная аналитика, потому что мне, чтобы доказать, что это не будет зависеть от разбиения единицы, надо переставлять интеграл с суммой. А это очень сложно, если сумма не конечная.
Окей.
Окей.
Там же локально конечно. Ну, конечно, в каждой точке, поэтому там можно
Ну да.
Нет, ну вроде все же так же.
Ну, вообще...
Это же у самой, ну это же относится к самому разбиению единицы, а там если потому что мы сумму хотим, чтобы она была конечной.
Ну, это сумма по картам. И там нулевые все,
но
кроме
все равно,
конечного числа.
не, но она по картам, но все равно на ну, я не знаю, все равно придется переставлять.
Ну, можно доказать, что всегда можно переставить суммой, которая в каждой
Ну, да,
точке только
я
конечная.
согласен, что там, если покопаться побольше, то можно это доделать. Я думаю, что это просто технически просто неразумно, мне кажется, для нас дальше углубляться. Я согласен, что там можно исправить в определенных случаях. Okay. So, right. So let's look at how to prove this. We just check for m equals to hn, and of course then dn is rn minus 1, right? And so I have omega is written as follows. It's sum over I from 1 to n, some functions. Omega I, then I have dx1, blah blah blah, and then dxi I just omit. Dxn. This form of degree that I need, any form on hn of degree n minus 1 looks like that. And then, in orientation, well, we need to choose orientation on hn. This will give us orientation on m, right? So choose orientation, well, just usual. D over dx, well, just this basis at each point. And then this will give us Stokes orientation in dm. Then I need to, okay, so then differential of omega will be like that. So I need to compute derivative with respect to xi, and then I will have dx1, which blah blah blah, which dxn, except I need some sign here, right? So I will have dxi here. I need to, pull it through how many I minus 1 elements. So I minus 1 here. Okay. And so therefore, if I compute integral over hn of d omega, this will just give me, well, okay, I need to also to assume after maybe rescaling the coordinates that support of omega is inside well, this. So I take negative 1, 1, n minus 1 times, right, times 0, 1. Just to make integral from negative 1 to 1 every time, except for the last coordinate, which I will have from 0 to 1. Anyways, so I have integral of the omega is, I will have sum over I, negative 1 to the I, and then I have bunch of integrals from negative 1 to 1. Right, well, the first one, let me write the first one to be from 0 to 1, this will be over dxn, and then all others from negative 1 to 1, so they are over dx1 blah 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 dxn minus 1, right? And then I have d omega I over dxi, right? And then d, well, just like that.
Excuse me, question about the support of omega.
Yes.
You said that this is after scheme, right? This is just the condition of the support being compact.
Yeah, we can put any R in here. I just don't want to carry.
This is just the condition.
So I can put, like, instead of 1, I can put R here. So I can.
So this is just the condition of compactness.
Yeah. So I'm using compactness here. Yes.
This is exactly it. This
Yes.
is just.
Yes.
Спасибо.
All right. Then, yes, I have this, and then I integrate. So I have derivative with respect to each xi, right? And so I also know that. Well, my form, it is so at negative 1 and 1, it should be actually 0, right? Because the support is inside, but if my x, well, say 1 of x1 through xn minus 1 is negative 1 or 1, then the corresponding form is just 0. Okay? And then, well, I integrate. I just take all these integrals, right? For if I fix I here, well, I just change order of integration such that dxi is first, then integrate. I will have omega I at xi equals to 1 minus omega I at xi equals to negative 1. So all this is 0. So if I is not in here, right, then the corresponding term is 0. So what I'm saying is now is that what is left is negative 1 to the power n, and then I have integrals from negative 1 to 1 of dx 1 blah 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 dx n minus 1, right? And then I have, well, I integrate the form with respect to dxn if my term, if I equals to n, right? Again, I have the derivative here, so I integrate it will be a value at xn equals to 1 minus the value at xn equals to 0. Okay, but at xn equals to 1, form again is 0, but the only non-zero thing that we have is from this 0. So I will have actually omega n x1 blah 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 x n minus 1 and then 0. So this is the left hand side of the Stokes theorem. The right hand side, well, I need to do what? I need to take integral of omega over dhn. So this will be, again, all that stuff. So I need to use the definition, what is an integration of omega over submanifold, right? So I need to pull back by inclusion of hn to hn. And so this would mean basically that, well, I have integrals from, so dhn, it just corresponds to xn equals to 0, right? So I'll have integral over all from -1 to 1, dx1, blah, 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 dxn minus 1. And then I'm pulling back my form to here, meaning that I just have to put, have to put sum over I here, right? Sum over I, and then -1 to the power I, omega I, x1, blah, 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 x, n, minus 1, and then 0. And then, yes, right. Yeah, by the way, so I don't have any sum here because, well, because I star, so I have an inclusion. Let me denote it like this, of dhn to hn, right?
Maybe use the notation of
So what I need, so let me be clear. So what I need is the pullback of I star of dxi is 0 for I equals to n. So let me, for I equals to n. So that's what I have, right? Because, well, xn corresponds on dhn, xn is just 0. So therefore I have this. It means that when I put my form omega and put it inside here, I need to pull this back by I, right? Which means if I have this term in here, it's gonna be 0. So the only surviving term is when I equals to n. So no sum here. That's one thing. So no sum here. And by the way, no sign, no anything. So I have this, and then omega n here. Sorry, omega n here. So that's what I have.
may I please repeat why in the left-hand side, only one term was left? Why the others modified?
Here.
Left-hand side, the previous.
Here because, well, when I integrate, when I take fix some I which is not equal to n, it will correspond to evaluating form. So it's like it will be integral of d omega I over dxi, right? From -1 to 1 dxi, we'll have this, right? Well, and other stuff, but I can, pull this to the right. But this is what? This is, I integrate now with respect to dxi, I will get omega I at anything where I put 1 on ith place, well, and all this stuff inside. Minus this, minus omega I at blah blah blah, and here at ith place I will have -1. But that's a value of omega at the boundary, should be 0. Well, because I know that form is supported inside, in particular closure of all elements which is not 0 should be inside here. So therefore, at -1, 1 should be 0. Except this boundary is actually, well, it's like this boundary does not make it like effort into closure, because it's already like because of subset topology, right? So anyways, so on this boundary, it should not be the form should not be 0. Only at -1 and 1's here.
So both terms are.
So both terms are 0.
Thank you.
Yes, and then we have this. Let's see. What's the difference? The difference is this sign, right? So that we just need to compare the Stokes orientation. Well, what Stokes orientation gives us, right? So I have two. So on DHN I have orientation, which is this one, negative d over dxn, and then d over dx1, d over dxn. So this is Stokes orientation by our definition. And versus what we have here when we computed this integral. When we computed this integral, we actually had. So the question is, what should I put in here? Plus or minus, right? So I need to right. So my order was, when I was computing this, is dx over dx. So when if I have plus here, then this basis is positively oriented. Well, I need to put right. Well, I need to put n here. Anyways, the sign in here, I'm claiming that the sign in here should be the determinant of passing through from this basis to this basis.
N-1, last diffusion in the first basis.
Yes, n-1, yes. N-1. Well, this is I need to compute the determinant of this, right? -1, and then I have 1, 1. Well, the determinant of this is -1 to the power 10. Because you have this -1 times 1. But then this -1 stays at the place, at the nth place, right? So when I, expand it by this column, I will have to put negative. So it's -1 to the power n-1, right? This n-1 because it's on nth place here, times -1 because this -1. And so this is this. All right. Then, okay, so we checked everything works for boundary, and that's the most non-trivial part. Then, well, when M is Rn and dm is just empty, well, it's just the same but easier, right? All terms will be gone. right? We had something left in the previous part, but now it's just 0 equals to 0. That's it. Now, and then, well, we need for any m, so m is any. Well, we need some computation. Let me do it real quick. So I'll have this. So I need to use the definition through the partition of unity. So I'll have this sum over sum I from J, psi I omega dm. Then this is, I need to pull this back to dh, right? So this will be a sum over I integral of, well, just by definition of my integral. Phi I, so again, I have ui, which is coordinate neighborhoods, and phi I charts, and psi I is a partition of unity subordinate to this ui. So as we had in the definition of integral, so I take phi I inverse and pull this guy back to where? To dh n, to dhn intersect phi of ui, phi I of ui. So I pull this guy back. Well, then we can just, because of psi I, we can extend this guy by 0 to the whole dhn, right? Because psi I, has support inside here, right? So I just extend by 0, I get sum over I integral dhn of this pullback. Then, well, extend by 0. By 0. But then this equals to, so I need to apply Stokes theorem for Hn and get the sum over I integral over Hn of t phi I inverse star psi I omega Hn. Right. So I need to compute this guy. So let me do it here. So differential commutes with pulling back. So I have d phi I star inverse. Right. Maybe too much parenthesis. Psi I omega. So this is phi I star inverse. Sorry, the other way. What am I writing? So I have to phi I inverse and then star, right? And here as well. Inverse and star. And then I have d psi I omega. So d psi I omega, well, it is this psi wedge omega, so we use definition for d, so defining property. Then I will have to write d psi I wedge omega plus psi I wedge d omega. But then, once I do all that, I can pull the sum inside, right? And when I sum over I will have, so I will have d, then sum over I psi I. So when I take the sum and pull it inside, I will have, and look at this term, I will get, sum goes through d, right? So I have this, but this is just 1. So this is 0. So this term is gone. When I look at this term, again, I pull sum inside, I will get sum over I psi I, which is just 1, right? So I will have phi I, and it's upon star of d omega, right? So the bottom line of all this discussion is that the result is integral over h over h n right. Well, it's just yes. Right. So how to write it in a better way? There's still in sum over I, phi I inverse star, right, psi I d. Well, this is just by definition of my integral. This is just integral over dm, right, of d omega. This is just definition of integral. And so we are done. Okay? And we proved Stokes' theorem. And let us wrap up with integration. And do you have any questions before we proceed?
Excuse me, the term psi times d double, this is just the usual multiplication, right? Psi is not a four-letter function.
Yeah. Well, we just defined, well, what is the wedge of a form with a zero form?
Zero.
It's just multiplication. I'm just like, I want to put inside wedge here because my defining property of d, I wrote it with wedge in between. So it looks more like defining property that we discussed.
D commutes with pullback.
Yeah, D commutes with pullback, but with wedge it uses gaping through. But in this case, when we sum over I, it's actually commutes with psi I also. All right, so now we start a new story, and which is connections on vector bundles. So connections on vector bundles. Well, suppose just definition right away. So let y e to x be a vector bundle. Then a connection I usually denote it by the symbol nabla on E is an R linear map from where to where? So it's sections on E to sections on E tensor T star X. Such that satisfying so if I take nabla of a function times section, so it's R linear but not C infinity over X linear. So instead of linearity with respect to C infinity of X, we have this condition. Nabla of function times section, you need to take, well, F times nabla of S plus S tensor df. For any F from C infinity of X and S from gamma of E.
Как мы умножаем гладкую функцию на сечение расстояния?
Ну, в каждом слое вот этой проекции умножайте на число, которое дает эта функция. Вот. Okay, so the idea is that you want to be able to differentiate a vector in some direction. So I don't know, maybe I need to draw a picture. So we have like an X. Right, and so this is at the top you have like E. Good.
What's the gamma?
Yeah, so it's a section of this vector one. Right. So you have like at the top you have some well, I don't know. Maybe it's not so wrong. So you have an element. So this is E, this is X, and so projection works like that. Right, and so if I have a point X, right, I want if I want to move it a little bit, right, I want to see how this point, like, actually I'm defining how this point moves if I move this point X. So this is like Q, and this is pi of Q. It can move like into this direction if I move it like that, or to here. So this so we will see in more maybe abstract terms that what I'm choosing is like a horizontal subbundle inside of some vector bundle. Anyway, so that's my choice of how the point moves if I move its projection in the base a little bit. You should think about that. So how to differentiate like this point with respect to x in some direction. So direction means that, well, it has some entry. So the result has some entry, which is like a direction of differentiation. So that's what the co-vector field is doing here, right? But we'll see as we work more with this notion. Well, I hope this will be more understandable.
May I ask a question? Is it true that both sections are over X? X is the base space. Yes.
Well, what do you mean section over X?
Sections from X.
Yeah. So by definition, if S is from gamma of E, S is a smooth map from X to E, such that its composition with projection is identity on X.
А вот как вот это вот определение, в смысле, что мы в каждой точке взяли, допустим, вот над X лежит Q, да?
Да.
Это сечение G от E.
Да.
А вот справа написано сечение какого-то тензорного произведения расслоений. Как это связано с вектором таким?
Связано с тем, что вот, грубо говоря, мы должны задать... То есть это такая универсальная штука, которая знает, как дифференцировать вектор в слое по какому-то направлению в базе. Вот. А направление в базе, это значит, что вы... Вот, это какая-то универсальная штука, вот, но если вы хотите задать направление в базе, вы должны его как бы, ну, значит, задать. И тогда у вас будет то, что называется ковариантной производной, но мы к этому придем. Значит, ну, давайте выберем. Это здесь должен быть тогда какой-то элемент там v из t, x, x. Правильно? Вот я
Можем
задал.
задать эту
Да,
форму,
вот,
да?
я его задал, и это значит, что вот этот аргумент скушает вот этот v,
Мгм.
вот, и у меня получится дифференцирование вот
Векторных
в направлении v. То есть вот это надо думать, что это аргумент, ответственный за направление, в котором я дифференцирую.
Ну, идею я глобально понял, а почему мы хотим, то есть мы хотим получить...
Это все, что я хотел.
Мы хотим пару векторов и его управления,
Да.
а почему между ними связь именно тензорных произведений? Не получится просто с одной суммой.
Ну,
Чем оно здесь полезно?
почему тензорное произведение? Ну, потому что...
Как получилось?
Нет, вы хотите, чтобы линейность была, по крайней мере. В прямой сумме не будет никакой линейности. Ну, то... Ну, вы хотите как бы дифференцировать в этом направлении, вы можете перескалировать вот этот вектор. Вы хотите, чтобы вся ваша как бы, производная умножилась на число.
Я сейчас, то есть в правой части мы, получается, берем вектор из сечения, и что в итоге получаем?
В правой части...
Ну, мы подставляем
Да.
туда, вот, и мы что в итоге получаем?
Ну, из сечения. То есть, если мы поставили что-то, какое-то векторное поле, вот,
Да.
но у нас Е, получится что просто элемент гамма от Е. Но мы это увидим, это как бы сейчас не то чтобы прям очень важно, главное, чтобы вот формально это определение понятно, да?
Ну, да.
И мотивация, как бы вот она такая. Это скорее, что может быть, к чему можно стремиться дальше, как все это разворачивается. Ну, я не знаю, как мотивация, как это можно понимать. Вот и все. Вот это абстрактная вещь. Но хотя вот это, ну, формально это имеет все значение, правильно? Вот главное, на данном этапе важно это. Да? Все буквы, понятно, что они значат. Ну, и почему я хочу, значит, ну, что-то типа Лейбница, чтобы выполнялось? Ну, потому что это будет вот производное. Okay. It will, as we will use it to construct more stuff like geodesics, parallel transport, I think this will be more clear why this object is like that. Okay. Yeah. So the question is. The question is what freedom we have at all, right? So how many connections are there on a vector bundle? right? So, and well, some answer to this question is given by the following observation. So suppose we have two connections on E. Then I can actually consider, well, the difference well, it's our linear map, so I can consider difference of our linear map. This makes sense, and then apply it to something like this, where again, if f is a function as is a section on E, then it can be checked just using this Leibniz rule that this guy is actually C infinity of x linear. So I can actually pull this f from this and get this. Well, just because this term will cancel. So therefore, I can think of difference between two connections as an element inside the gamma of E star tensor E tensor T star X. Why is that? Just, you know, side explanation so that we have some map. So I'm saying that such a map defines a section, well, like that, if and only if it is C infinity of x linear. So let me formulate this. So we identify.
Вроде пространство отображений, да, линейных, оно как-то является чем-то расслоением.
Ну, да, то есть вы можете какое-то отображение выбрать. Вот давайте, я сейчас это аккуратно скажу. So, we identify вот, C infinity x linear map f well, from some vector bundle to another vector bundle. In this particular example, this another vector bundle would be E tensor T star X with section on of E star tensor E tilde as follows. So, well, a section, if my map is F, the corresponding section, let me call it S, and then I say that, okay, S should be from X to here, right? And then well, I define it like this. From point P in X, I map it. Again, I'm using like this triple notation, right, that I defined for when we considered like a clutching data. So a class of the triple P, U, and sum over E I tensor F of E I P. Sorry, and here we have star, like that. That's like a concrete way how I identify section in here, entire linear map in here. So EI is just some basis on Rn, right? I can say that, okay, EI is local section, so f of EI gives me a local section here, and I consider the corresponding value at the point P, right? So that's what it is. And so really, for this thing to be independent of the choice of basis EI on Rn, it should be C infinity of x linear. It's just exercise, or you can see it right away. I don't know if you're used to such kind of expressions.
Это можно стать этими коциклами, доказать, что они одинаковые.
Ну,
Если два расслоения, то гомоморфизм с одного в другое.
но даже внутри одной тривиализации вы же можете по-разному выбирать базис сечений. Вот это не зависит от базиса сечений, зависит только от f. Вот, это тоже доказывать, ну, для доказательства этого необходимо, чтобы f была c бесконечно от x линейно, не только r линейно. Вот. Ну и понятно, что если у вас f разные, то и, соответственно, сечения разные. Но и обратно тоже, любое сечение вот этого, ему можно поставить c бесконечно линейную функцию. То есть вот, значит, c бесконечность от x линейной функции между вот двумя пространственными сечениями то же самое, что сечение вот такого векторного расслоения. Окей. Was that? Можете по-русски, да, извините. Да.
Yes волной.
Yes волной, ну, это я как бы в общем сказал. Yes волной, это в нашем случае это вот это. Вот, короче, значит, разговор тут такой, что если у меня есть, if I have two connections, then they differ by an element, by a section of this bundle. And the other way around, if you have, so conversely, if nabo is a connection, and then and also you have some, I don't know, S, which is section of E star E tensor T star X, then nabo plus C is another connection. Anyway, so you have some, so the message is that a connection is something more complicated than just like a section of such thing. So it's like well, it's actually, you will see.
Нужно плюс S.
Yes, plus S. Okay, so what else can I? Then I need to introduce Christoffel symbols, which is kind of time-consuming. So I assume we'll just stop here. Okay, not bother going. Да, на следующей неделе не будет ничего. Зато я бы хотел, чтобы мы на сессии у нас не будет никакой контрольной, но будет просто занятие вместо следующего.
А контрольный у нас когда будет? Когда?
Не будет контроля.
Можно формулу?
Да. То в конце будет экзамен, ну и семинар. Все, это все. Да.
А какая формула там с Уильсоном?
Ну, пример половины семинар и экзамен, но просто еще плюс 1 балл, как бы это девятка вам. А десятка это если вы более-менее все задачки на семинаре. Где-то